Audio Jungle. Audio Jungle.
Hello everyone, myself Narendra Maurya and hope you all are doing well. So guys, today we'll solve jet propulsion gate 2020 problems, right? And here we have problem number 15 for 1 marks. So in aircraft engine thermodynamics cycle analysis, perfectly expanded flow in the nozzle means that the static pressure in the flow at nozzle exit is equal to first, the stagnation pressure at the engine inlet. Second, the stagnation pressure at the nozzle exit. The third is the ambient pressure at the nozzle exit. Fourth one is the static pressure at the nozzle inlet. So we'll get the correct answer for this. First, we'll go this word perfectly expanded flow. Okay, so this perfectly expanded flow, perfectly expanded, or it is also called optimally expanded, or it is also called fully expanded case. Okay, so that meaning is simple. Exit pressure of the nozzle is equal to ambient pressure. So you make a remark point. All right, this is the remark point. Okay, whenever they will say perfectly expanded or fully expanded or optimally expanded, so immediately you need to understand exit pressure is equal to atmospheric pressure. Now I will show you that diagram, symbolic diagram of aircraft engine, so it will be more clear. So just say this is what compressor, combustion chamber. This is the symbolic diagram only, and this is what turbine. Okay, compressor. This is what combustion chamber, and this is turbine. All right. This is the cowling part. All right. Now I must say this is the flow inlet here. Check. This is the flow inlet atmospheric here. So just say A. This is 1. This is 2. This is 3. This is 4. And this is 5. Or also it is called exit. Okay. So here we have anyway. So this part called inlet or diffuser. This is compressor, combustion chamber, or this is turbine, and here this is nozzle. All right. If you draw the TS plot for this, in short, I will show you. Okay. So you just say this is A, 1, 2, 3, 4, and here we have a 5 or exit. Okay, and this is Isentropic points. Okay, isentropic point. So exit is what, phi or E? So for fully expanded case, this PA is equal to PE. So what is the mean of it? You can say that exit pressure of the nozzle is equal to inlet pressure of engine. That will be called a fully expanded. Okay, or it is called optimally expanded case. Okay, always remember. So here that option, if you read, the static pressure at the nozzle inlet. Okay, this, they are saying the nozzle exit is equal to the stagnation pressure at the nozzle inlet. Okay, the stagnation pressure at the nozzle exit, the ambient pressure at the nozzle exit. Okay, the static pressure at the nozzle inlet. So whatever the static pressure at the nozzle inlet, that will not be possible. Nozzle inlet, they are saying that is not possible. Ambient pressure at the nozzle exit, that will be correct, because they may say like engine static pressure, but here it is given stagnation pressure at nozzle engine inlet. That will be wrong. Okay, because the aircraft engine thermodynamic cycle analysis perfectly expanded flow in the nozzle means that the static pressure in the flow at the nozzle exit. So static pressure will be equal to static pressure, not stagnation pressure. So first and second, these two are wrong. Okay. Third option they have given the ambient pressure at the nozzle exit and the static pressure at the nozzle inlet. So nozzle inlet pressure, you just think this is suppose nozzle. So here this is the nozzle inlet pressure and this is nozzle exit. So this PA and here nozzle inlet pressure is what? Check. What is the nozzle inlet pressure? What is the nozzle inlet pressure here? See, nozzle inlet pressure is not 4. So 4 static pressure at 0.4 will not be is equal to exit of the nozzle. So exit of the nozzle PE will be equal to ambient pressure at exit nozzle, because here whatever the pressure at the exit, it is PE, and obviously outside the surrounding pressure will be what? PA. So that will also, because here this is PA and this will also be PA because it's the surrounding pressure. So you can say the static pressure at the nozzle inlet, that will also be wrong. The ambient pressure at the nozzle exit will be correct. Ambient pressure or a surrounding pressure or atmospheric pressure. So PE is equal to PA. Hence, what is the correct answer? Option C. Hope you understood. Answer is C. All right. Remember, perfectly expanded or optimally expanded or the fully expanded. Okay. That meaning is what same. Always remember. All right. There should not be any confusion. That meaning is what? Always exit pressure is equal to ambient pressure or surrounding pressure. And that ambient pressure or surrounding pressure will be equal to exit pressure. Okay, always remember. So ambient pressure, it is maybe inlet of the diffuser. If they say engine inlet, but it should be static pressure here, but here it is given stagnation pressure, so that will also be wrong, because engine inlet pressure is what? Always ambient pressure. So instead of option C, option A can also be correct, but it should be static pressure, but here it is given stagnation pressure, hence it is not correct. It should be static pressure at the engine inlet. That will also be correct, because engine inlet pressure is also atmospheric or ambient pressure. But it is a static pressure, not a stagnation. Here it is a stagnation, hence option A is wrong. Hope you understood why option C is correct. PE is equal to PA. That means ambient pressure at the nozzle exit. Simple. The nozzle exit pressure equal to ambient pressure at the nozzle exit. That will be correct answer. So this pressure PA is equal to exit. So at the exit also the same atmospheric pressure or ambient pressure, if it is there, then it is the fully expanded. Okay. Another case also, two case I will write here, case 1 and case 2. Case 1 is what? Uh, One is overexpanded case. Further, you need to remember this, okay? And under expanded, under expansion or under expanded case. So another two special cases we have. Maybe they can ask, okay? So this is the remark point. Your answer now, your answer is already finalized. Your answer is what? C. In this problem, it is decided, okay? Because exit is equal to ambient, and that you got ambient pressure at the nozzle exit is equal to static pressure at the nozzle exit. That is true. Now further discussion I am telling you, for overexpanded and underexpanded case also they can ask. So in case of overexpanded, always remember will get oblique shock. This is very important. They can ask, okay, oblique shock you may get. And underexpanded, expansion fan. Okay, expansion fan. This is very important. For that reason, I have written here. So you should know overexpanded and okay. So in this over expanded case, you will have exit pressure will be less than ambient pressure. This is the over expanded. And under expanded means PE greater than PA. Always remember three things I told you. Okay. Case 1, 2, 3. I must say this is case 2. This is case 3. Where is case 1 then? This is case 1. Okay. So case 1, 2, 3. Remember it because it is very uh, like a frequent question they can ask. Case 1, fully expanded, optimally expanded, or perfectly expanded. In this case, PE is equal to PA. This is called fully expanded. Case 2, over expanded means PE less than PA. This is called over expanded. Okay. Case 3, under expanded. Over expanded. In over expansion, you may get oblique shock. This is 1 marks question they can ask any times where PE less than PA. Under expanded expansion fan, you may get what is expansion fan, what is oblique shock. That is the further discussion I will do later. But you should remember, okay, under expanded means PE greater than PA, which and in case of under expansion, you may get expansion fan. For all right, okay, okay, done. So here your answer is option C. Anyway, now we'll go for next problem. Check. This is the next problem. Here we have to do. This is problem number 47, right? It was asked for 2 marks. Here this question is what? Basically, check the design flight Mach number of an ideal ramjet. So this problem is what? Based on ideal ramjet. Engine is 2.8. Design Mach number. So first we'll write given data. Design Mach number for the ideal ramjet is 2.8. Obviously it is supersonic, and you know very well ramjet engine is what used for the supersonic flow, right? The stagnation temperature of air at the exit of combustor is 2400 Kelvin. Okay, stagnation temperature. Assuming the specific heat ratio gamma is given 1.4, and gas constant, which is characteristic gas constant R, it is 287 joule per kg Kelvin. Okay, velocity of air at the exit of the engine, VE, need to calculate. V exit, we need to find. All right. So in the given data, they have given temperature, stagnation temperature. Stagnation temperature means T naught. Okay. Exit of the combustor. So wherever the combustor we will have, that exit of the combustor temperature is given 2400 Kelvin. Huge temperature, right? Anyway, so where T naught I have written, numbering I will show you. So check this diagram. This is what? A ramjet. Yes or no? So for this ramjet, where is the combustor? Check. This is the combustion chamber, and combustor exit is what? This is the exit of the combustor. Yes or no? From here combustion, this is the combustor full. Up to here, this is what? Combustion chamber. Yes or no? This is the exit of combustion chamber, and this is the inlet. Inlet of combustion chamber. Yes or no? So basically, exit of combustion chamber, total quantity we need to write T naught 4. No? So I must say this is T naught 4. Hope it is clear now to you. For the ideal ramjet, you know very well, ideal ramjet means it is a adiabatic reversible adiabatic or isentropic, that is called ideal. Yes or no? So ideal ramjet, it means no pressure drop. No pressure drop. Yes. So what is the mean of it? Here we have total. This is the static pressure, obviously at point A, but total pressure also you can write P naught A. This P naught is equal to P naught A. That must be equal. P naught 2 we have. This is P naught 3. Okay. Pressure is what? P naught 4. This is P naught 6 or P naught exit. That is the ideal ramjet. Temperature will also, you can say T naught A. This is what? T naught 1. All right. This is T naught 2. Okay. And this is what? T naught 4. Okay. And this is what? T naught 6 or T naught. So no pressure drop means total pressure must be same. No pressure drop means total pressure. Total pressure must be same. And total temperature also must be same. In diffuser, or this is the diffuser part, right? This is the diffuser part. A21 is supersonic compression. This is diffuser. Here it is given, check everything. Combustion chamber and in nozzle. So in diffuser and nozzle, no heat, addition or rejection, hence total temperature must be constant. So you can say T naught A is equal to T naught 1 is equal to T naught 2. And in nozzle, where is the nozzle? Check. Nozzle is from T naught 4 to T naught 6. So T naught 4 is equal to T naught 6, or it is also is equal to exit. But what about combustion chamber? Check. Combustion chamber is what? T naught 2 and T naught 4. So that T naught 2 does not is equal to T naught 4. Why? Because it is a combustion chamber and we are adding heat in combustion chamber. We are burning fuel, so heat is being to be added. Yes or no? So that total temperature will not be same. That's the mean of it. That is the condition I am telling you. Okay, for ideal ramjet, and total pressure must be same. P naught A is equal to P naught 1 is equal to P naught 2 is equal to P naught 4 is equal to P naught 6 is equal to P naught. Means total pressure must be same throughout the engine, okay, because it is ideal ramjet. There is no shock formation. Hope you understood this. Yes or no? Hope you understood this. And another for ideal ramjet condition, MA must be equal to ME. So these are the criteria, okay, for ideal ramjet. What is MA? MA is the Mach number for the inlet flow, and ME is the Mach number for exit flow. It is ideal ramjet, hence MA is equal to ME. This is the one kind of proof. I am not doing that proof because here derivation is not important. Understood? All right. I hope you understood this. Now they are asking what is the velocity of air at the exit of the engine. So we'll use the concept because total temperature they have given T04. So that T04 will be the exit of combustion chamber, and this T04 will be equal to T06, and T06 is equal to T0E. Okay, it means they have given, okay, it means they have given T0E. How much it is? T0E, how much? It is 2400 Kelvin. 2000, this temperature they have given to you. They have given the Mach number also, design Mach number, and this as per ideal ramjet, MA is equal to ME, and what is the Mach number they have given? Check 2.8. 2.8. Yes or no? This is the value. Now, because it is ideal ramjet, there is no shock formation. Okay. In fact, because this is 2.8 is what supersonic. Yes or no? And for the supersonic flow, definitely shock should form. Oblique shock or normal shock, but shock should form. But it is ideal ramjet. Ideal ramjet means no loss. Okay. Ideal means no loss. Yes or no? Ideal means no loss, means no shock formation. You need to remember. So we can apply isentropic relation. Yes or no? Isentropic relation we are free to apply. Just think, if it is not ideal ramjet and Mach number is what 2.8, means shock will be formed there. If shock is what forming somewhere, so you cannot apply isentropic relation. You remember this, okay? But here you are free to apply isentropic relation. Why? Because it is ideal ramjet and there is no shock formation. All right. What is the isentropic relation? Isentropic relation is very clear. T naught E divided by T. Total temperature divided by static temperature is equal to 1 plus gamma minus 1 by 2 ME square. What is the ME? Exit Mach number. All right. Now, T naught E they have given to you. How much? 2400. ME they have given to you. You can calculate TE. Yes or no? So, and gamma is also given. How much? 1.4. Check. Gamma is also given 1.4. All the data they have given to you. We'll calculate, we'll put all the value and we'll calculate TE. I will write this. So TE is equal to T naught E, which is 2400 divided by 1 plus gamma 1.4 minus 1 by 2. ME is 2.8 square. Let me solve this. You also solve. So 1.4 minus 1 divided by 2, 0.2 into 2.8 square 1 plus answer 2.56 2400 divided by this. How much? 934. 934.57 Kelvin. So TE we have now. Okay. What is the TE? Let me complete here only. TE we have. What is that? 934.57. So here only I can use the relation. They are asking the exit of the engine. Okay. Exit of the engine they are asking. So I can solve here. Just let me erase this part. Okay. And I will write this T04, which is 2400 Kelvin. Okay. So we have T0E, which is nothing but 2400 Kelvin. I told you, yes or no? Because T04, which is exit of combustion chamber temperature, and that will be also equal to total temperature at exit of nozzle. And T just now you have calculated how much it is. 934.57 Kelvin. You know what is the total temperature? That relation, you know what is that? T naught is equal to Te plus VE square divided by 2 Cp. Okay. For the air, you know, Cp you can calculate here. Okay. What will be the Cp? Cp is nothing but gamma R divided by gamma minus 1. If you write what is the gamma? 1.4 R 287 divided by gamma minus 1.4. It is 1004.5 joule per kg Kelvin. So this is R value, Cp value. Okay, we'll keep here. So we'll calculate what is the V exit. Okay, what is the V exit? Check. V exit will be 2 Cp T naught E minus Te. We'll calculate this all value we have. Okay, so Cp I have multiplied by 2 in bracket, again multiply, in bracket we write 2400 minus 934.57 is very huge value. This velocity is nothing but 1715. Okay, 0.82 meter per second. So what is the velocity? 1715.82 meter per second. Round off to one decimal place means 1715 if you write, or round off to one decimal place, so you can write 1715.8. This is also correct. Hope you understood this. This is the answer. All right. Now, so this is problem number 48, same gate 2020, right? So we'll read this problem. The operating condition, okay, the operating condition of aircraft engine combustor, okay. So aircraft engine combustor. So one segment they have given, okay, which is combustor. So we'll talk about combustor as follows. So all the information here, it is related to combustor. They have given what they have given. Number one, the rate of total enthalpy of air entering the combustor 28.94 megajoule per second. So this is the total enthalpy of air entering. All right. Second, the rate of total enthalpy of air leaving. Better to say it's not air, better to say gas, because whatever the products will leave from the combustor, it is not only air, it is air plus fuel, which is called gas. Okay, because gas means air plus fuel, and that is true also. This products will leave the combustor. So this air, from my side I will suggest this is not air, this is gas. This should be gas. Okay, all right. And third, the mass flow rate of air they have given 32 kg per second. Air to fuel mass ratio 15.6. Lower heating value of fuel they have given, and they are asking what is the efficiency of combustor means they are asking efficiency of combustion chamber eta cc, efficiency of combustor or combustion chamber. All right. So this is one segment they have given for the aircraft engine combustor. So as we know, if you'll go for the combustor, okay. So this is the combustion chamber, I would say, okay, and this is combustion chamber. I can give the numbering also, standard numbering, like for the jet engine, the numbering. What is the numbering? It is you say like this is what compressor, combustion chamber, turbine. Yes or no? And this is very generic. This is nozzle, and this is what diffuser. So flow is what entering here, and flow is what leaving here. So this station is what A to 1 diffuser, 1 to 2 it is compressor, 2 to 3 it is combustion chamber, 3 to 4 it is turbine, and 4 to 5 it is exit. Yes or no? You all know that this is compressor. Here we have a combustion chamber CC, and this is what turbine. This is what nozzle, and this is what inlet or diffuser. This is standard numbering. So for combustion chamber, okay, 2 to 3 is the combustion chamber. Here this is what combustor. This is the standard numbering. Hope you all understand. So I would say this is 2 and this is what 3. Yes, this is the engine inside part, so I will consider total quantity. So I must say this is not 2 and not 3. In combustion chamber, what happening? That air, fresh air you are getting from compressor. So obviously that air will enter here. This is the air, which is nothing but m dot a, and you will add fuel in combustion chamber. So this is the fuel you are adding here, okay, which is nothing but m dot f. And obviously in combustion chamber burning occurs, okay, combustor will combust the fuel, so you will have m dot a plus m dot f. This is what all about combustion chamber. Now we'll see what quantity they have given. Okay, they have said the rate of total enthalpy of air entering the combustor 28.94 megajoule per second. Okay, so I would say total enthalpy, rate of total enthalpy. So for my numbering, according my numbering, it is not 2. So h not 2, h not 2, okay, I would say dash. What is the mean of it? It's a rate of, rate means per unit time, rate of total enthalpy of air entering to the combustor, that is h not 2 dash, which means not 2 is the station, not 3 is the station, not 2 is the entering station, not 3 is the exit station of the combustor. Okay, h not, why I am writing capital H? Because it is the total enthalpy, it is not a specific enthalpy, total enthalpy, and it is given to 28.94 megajoule per second. I must write here 28.94 megajoule per second. Okay, or you can write 28.94 10 to power 6 joule per second. You can write like this also. Similarly, next quantity what they have given, they have given the rate of total enthalpy of gas leaving the combustor. Okay, so I must write H, station number is not 3. Why I am writing dash? Because it is per unit time. Why it is capital H? Because it is total enthalpy, hence this is nothing but rate of total enthalpy of gas leaving from combustor. Yes or no? All right. What is the value here? It is given. We'll check. This value is nothing but 115.42. Huh? It is nothing but 115.42 megajoule per second, or 115.42 10 power 6 joule per second. Another quantity what they have given, they have given mass flow rate of air, okay, which is nothing but mass flow rate of air, which is nothing but m dot a. So mass flow rate of air, which is nothing but m dot a, how much it is given? It is given 32 kg per second. 32 kg per second. This is the another quantity. What is the another next quantity they have given? They have given air to fuel mass ratio. It is air to fuel called A by F ratio, which means air to fuel means m dot A divided by m dot F. How much it is given? It is given 15.6. It is given 15.6. This is the ratio. All right, sir. Now we can check. They have given m dot 32 kg per second, and they have given m dot A divided by m dot F. How much it is given? 15.6. So we can calculate m dot F. Why I am calculating? Because once you write energy equation across the combustor, so that time you have to use mass flow rate of the fuel. Let me calculate this. It is 32 divided by 15.6. How much it is? 2.051. It is nothing but 2.051 kg per second. So all data you have. All right. Heat value they have given. How much it is? Heat value, check. It is nothing but 46 mega joule per kg. It is 46 megajoule per kg. Now we'll write energy balance across combustor. So check, it should be very clear. Combustor, here station 2, here station 3. Already I have given the diagram, but once again I will give so that there should not be any confusion. Here we have m dot A, okay, and here we have fuel, and here we have here we have gas, m dot A plus m dot F. All right. Now we'll write the equation, energy equation. So what is the energy equation? You all know total heat input is equal to total heat rejection. So what is the total heat input? I must say total heat input is nothing but m dot A into enthalpy, which is nothing but H naught 2, okay, H naught 2, or in terms of because capital you are writing, so you can write capital H naught 2 because rate they have given. No? So we'll write the same thing so that it should be very clear. Okay. Wait. All right. H naught 2 dash plus, this is the fuel, m dot f into combustion chamber or combustor efficiency eta cc into, they have given heat value, is equal to m dot a, m dot f, all right, into what is the enthalpy at naught 3, h naught 3 dash. Okay. We'll check the unit. Unit balance is very important. Any unit balance you can check. Better we'll check this unit. Why I'm checking the unit? Generally it is not required, but here you can check. They have given the different form of the unit. See, here it is given megajoule per second, but here it is given megajoule per kg. So for that reason, this is kg per second, it's okay. So they have given different units. So better we'll find proper unit, we'll change the unit, and then we'll calculate. Okay, it should be dimensionally balanced. All right. What is the unit of this m dot f, mass flow rate of fuel? It is nothing but kg per second. Eta cc is the efficiency, which is dimensionless. Heat, and heat value is given megajoule per kg. Yes or no? Check megajoule per kg. Megajoule per kg. See here. This is what megajoule per kg. All right. So we'll change this unit. Megajoule per kg. Cancel out kg and kg. What you will get? Megajoule per second. Okay, now this unit megajoule per second. So obviously h naught 2 dash, check h naught 2 dash. What is the h naught 2 dash unit? See, it is megajoule per second. So h naught 2 dash is okay, it is megajoule per second. But here check. Here. So h naught 2 dash is what? Mega joule per second is there, but in multiplication it is m dot a, which is kg per second. Similarly here also h naught 3 dash also unit is mega joule per second. Okay, and this is kg per second. You check h naught 3 dash unit is 3 megajoule per second. Yes or no? So but I should have a same unit, like check this, we'll have a 3 component, 1, 2 and 3. All 3 components should have a same dimension, so you can convert in any form. Better you follow middle one, which is megajoule per second. So we'll convert this first also in megajoule per second. So first we have, what is the first? This is m dot h naught 2 dash, it is kg per second, it is h naught 2 is megajoule per second. Okay, megajoule per second. What I want, check megajoule per second. What I want megajoule per second only. So better what you will do, you just, if you want this unit only megajoule per second, so better whatever you have I, that you can write m dot a h naught 2 dash, divide by, again you do m dot a. So you will have a megajoule per second unit, check, into megajoule per second, divide by again mass. Yes or no? You can cancel this. So you will get megajoule per second. Balanced. Similarly, I2 is okay. What about I3? I3 is what? M dot A plus M dot F into H naught 3 dash. If I will divide again m dot A plus M dot F, so the same you will get unit megajoule per second. All will have a same dimension, okay, unit, which is megajoule per second. So energy is what? Balanced. Only I am changing the dimension. So if dimension I am changing, then all 3 components should have a same dimension. Doesn't matter it is megajoule per second or it is megajoule per kg. It's your choice. but all dimensions should have same. So now the again same equation I can write. Check. I can write the equation now. M dot a h naught 2 dash divided by m dot a plus m dot f eta cc into heat value is equal to m dot a m dot f divided by, so that dimension must be same into h naught 3 dash. If you check the unit, all component will have a megajoule per second. All right, now check. M dot a, m dot a cancel out, m dot a and this value will be cancel out. So what you will have, h naught 2 dash plus eta cc heat value, okay, into h naught 3 dash. What will be the value of combustor efficiency? Eta cc is equal to, it will be h naught 3 dash minus h naught 2 dash, okay, divided by mf into heat value. I hope you all understand this. Okay, now we'll write combustor efficiency, which is nothing but h naught 3 dash minus h naught 2 dash divided by m dot f into heat value. What is the h naught 3 dash? Check. H naught 3 dash, it is 115.42 megajoule per second, okay, or 115.42 into 10 power 6 joule per second. Yes or no? So we'll write all the value here, whatever it is given. So this is nothing but 115.42 10 to power 6. Yes or no? This is the value into, next is nothing but h naught 2 dash. What is the h naught 2 dash? Check. H naught 2 dash is nothing but, see here, h naught 2 dash is 28.94 into 10 to power 6, 28.94 into 10 to power 6. M dot f you have calculated how much it is. Check. Somewhere you have calculated 22.0151. Check. This is the value, 2.051. And this heat value, how much it is? That value of the calorific value it is called, or heat value it is called. Okay, it is HV is called heat value or calorific value, meaning will be same, which is nothing but 46. Check. I think 46 megajoule per kg here it is given. Check. Megajoule per kg. Now you, because unit is balanced, so no need to change it. Same thing you have to write 46 10 to power 6. You calculate this value. We'll check. Wait. It is nothing but 10 to power 6 10 to power 6. First of all, it will be cancelled out. So 115.42 minus 28.94, okay, divided by 2.051, all right, divided by 46. It is coming 0.9166, or you can write 91.66%. This is the fill in the blank. Let me check. It is percentage, so 91.66 you have to write. If it is not percentage, then 0.9166 you have to write. Percentage they have given, it means it is 91.66. This will be your answer. Hope, because so much segments I have taken here separate, because it was the mismatching of the dimension unit. Okay, but if you once you solve for gate, because you have to solve within 3 or 4 minutes that question, okay, maximum. So for that time, immediately you just use calculator and within finish you this unit change and equation of the energy across the combustor, directly unit change you can finish within seconds. It will not take so much time because I was explaining the question, so it has taken so much time. Okay, but you can finish. So why I have elaborated fully this component one, two, three, everything I have written, so that easily you can understand like what I want to tell you and what they have given in the problem, like change of the unit they had given, so that the student may get confused. But here already every steps I have explained, so I think like now you may not have any kind of doubt for this particular question. Okay, all right, so this is solved. So still if you may have any doubt or any confusion for any steps, for any like calculation or any equation, so you write comment on comment box. Okay, and all right, so this is done. So like and subscribe the channel, guys, so that whenever I will upload video you may get the notification, you know that. Okay, all right, so thank you all, thank you so much.